Hey everybody, welcome to Axiom. Today's topic is AVL trees from data structures. Now, I know this sounds intimidating at first, but I promise you, it's actually really intuitive once you see it the right way. Let me walk you through it. The typical promise of a binary search tree is efficient data retrieval. When data populates the tree uniformly, the structure grows outward in equilibrium, allowing search algorithms to discard half of the remaining data at every step. This yields a retrieval speed that scales at a logarithmic rate or O log n. That efficiency relies on a critical assumption that incoming data arrives in a random order. In practice, data frequently arrives pre-sorted or sequential. When you insert a sequential dataset into a standard binary search tree, values like 10, 20, 30, and 40, the sorting rules force each new node to the right of the previous one. The tree fails to branch, forming a straight line. Structurally, this is no longer a tree, it is a linked list to find a value at the bottom. The algorithm must now inspect every single node along the way. Search times drop from a logarithmic curve to a linear crawl, or ONA data structure that relies on the randomness of its inputs will eventually degrade. Maintaining performance in dynamic environments requires an active mechanism for structural self-management. In 1962, Georgi Adelson-Welsky and Evgeny Landis introduced the AVL tree. It was the first rigorously self-balancing data structure designed specifically to prevent this linear degradation. The AVL tree prevents structural collapse by enforcing a strict mathematical invariant on its shape. After every data insertion or deletion, the tree calculates its internal state and realigns itself to maintain equilibrium. Understanding this system requires looking at two distinct layers. First, the mathematical height bounds that define balance. Second, the localized pointer manipulations known as rotations that physically enforce those bounds. The AVL algorithm applies rigid localized rules to individual nodes. This is intended to constrain the height of the entire structure, keeping search speeds logarithmic regardless of how the data is ordered. The AVL tree relies on a specific relationship between local structural invariants and global system behavior. Mastering the mechanics requires looking past the code to the underlying geometry. The specific local rule that governs the AVL tree is the balance factor. For any given node, this is simply the height difference between its left and right subtrees. In a valid AVL tree, this factor must remain strictly at -1, 0, or 1. When a new node is inserted, it can increase the height of a branch. If the left subtree grows to a height of 3 while the right remains at 1, the root's balance factor spikes to 2. A balance factor of exactly 2 on -2 is an invalid state. This immediately pauses the insertion process to trigger a rebalancing operation. The balance factor acts as an embedded sensor network. It flags structural vulnerabilities at the individual node level before they compound into system-wide failure. The critical theoretical question is whether this local -1-to-1 rule is enough. Does it actually prove that the total tree height will never exceed O of log n? This sequence of minimal AVL trees from A to E bounds the absolute worst case scenario. We construct a tree with the absolute minimum number of nodes possible for a given height, h, where every parent subtree is different height by exactly 1. We can express the minimum number of nodes, n of h, as the root node plus the minimum nodes of its two subtrees, one of height h-1 and the other of height h-2. Because the h-1 subtree is larger than the h-2 subtree, we can simplify the relation. The total nodes at height h is strictly greater than twice the nodes at height h-2. Taking the base 2 logarithm of both sides completes the proof. The height of the tree h is strictly bounded by 2 times the log of the total number of nodes. If even the most imbalanced worst-case valid AVL tree is capped at O of n, then every valid AVL tree is mathematically guaranteed to execute searches at logarithmic speeds. With the math established, we look at the mechanics. The tree enforces its invariant using constant time pointer manipulations called rotations. In the right insertion case, a sequential sequence 55, 66, and 77 creates a purely right-heavy imbalance. The root node 55 registers an illegal balance factor of -2. To resolve this, the algorithm selects the middle node 66 to serve as the new pivot point for the subtree. The algorithm breaks the parent link and executes a left rotation, promoting the middle node to the parent position. The original root 55 is pulled down to become the new left child of the pivot. This transformation preserves the binary search tree sorting rule. 55 is smaller than 66, so it sits correctly on the left while 77 remains on the right. A single rotation is the mechanical bridge to the mathematical invariant. It requires only O of 1 time because it only involves shifting local pointers. A single rotation cannot resolve every state. Nonlinear insertion patterns create zigzag shapes that require a more complex approach. This is a left-right imbalance. The root node 55 is left-heavy, but its left child 15 is right-heavy because of the new node 33. A standard single right rotation fails here because node 33 is larger than 15 but smaller than 55. Simply promoting 15 creates a structural collision. The algorithm executes a double rotation. First, it applies a left rotation to the child nodes 15 and 33, straightening the zigzag into a pure left heavy line. Second, it applies a right rotation on the root 55, promoting the middle value 33 to the top. The resulting structure is perfectly balanced. 15 and 55 now sit as the valid children of 33. Double rotations demonstrate the algorithm's robustness. Regardless of the insertion pattern, a maximum of 201 polymether shifts will restore global equilibrium. In software engineering, strict mathematical perfection incurs a computational cost. The AVL tree's structural rigidity makes it a specialized tool for specific workloads. Compare the strict AVL invariant, where height differences cannot exceed 1, with the relaxed balancing of a red-black tree. A red-black tree allows its longest path to be twice the length of its shortest. Because the AVL tree enforces the strictest possible height balance, it yields the fastest lookup times in its class. In any search, the algorithm traverses the fewest number of nodes before reaching its target. This search speed is paid for during the writing process. The AVL tree's strictness requires more frequent rotations every time a node is inserted or removed. These traits define where these structures are used. AVL trees are preferred for read-heavy environments like database indexing. Red-black trees are more common in write-heavy language libraries, like the C++ standard template library. Selecting a data structure is about aligning a mathematical trade-off with the specific read and write profile of the system. The journey from a vulnerable binary search tree to the AVL tree highlights a shift from passive data storage to active structural protection. Global efficiency is the result of local vigilance. Every node monitors its own balance factor, triggering specific rotations the moment a threshold is breached. Mastering computer science requires understanding how micromechanics, like local pointer rotations, dictate the macro behavior and time complexity of massive systems. The AVL tree proves that predictable, scalable performance requires strictly enforced structure. Alright, that was AVL trees explained from start to finish. If you found this useful, smash that like button and share this video with a friend who's also studying for exams. Subscribe to Axiom for more lectures like this, and I'll catch you in the next video. Take care.